c'è. Non funziona mica. Non mi sembra funzioni. Vabbè. Aveva bisogno di una aiutina.
We can go for the second round of germanium diodes.
Yes. Okay. So yesterday I recollect the history of germanium experiment, starting from the first experiment in the middle of the 60s of last year, and then following all the history and ended with the claim and disclaim of the Heidelberg-Moscow result, final result. So now what I would discuss today is mainly in which manner Gerda analyzed its data, so the various steps up to the end, following the trajectory of how the data collected by this experiment produce the final result of discussing all the analysis cuts. So yesterday I briefly introduced the Gerda setup. The Gerda setup is made of a large water tank filled with ultra pure water in order to absorb neutron and also tag the muon entering in the detector thanks to photomultiplier all around the walls and the pavement of the water tank, and the principle is to detect the Cherenkov light. Then there is a large, in the middle of this water tank, there is a large cryostat filled with liquid argon, which works as a coolant and shielding. And then in the middle of this cryostat, there is the liquid argon Vito instrumentation made of two types of photodetectors. On top and in the bottom part, there are photomultipliers, and all around the string of the detector, there are wavelength shifting fibers read out on top by SiPM, silicon photomultipliers. Inside this Vito, there are the strings of germanium detectors. Here you see a sketch. Here are all the strings of containing the detectors of various type, as we will see later. These detectors are placed naked without the usual cryostat, which is a typical layout of the germanium detectors, are minimizing the material near the detectors and putting the only material of very high quality in terms of low content of radioactivity nucleus. So the material are selected in order to be very pure. We use very clean, ultra pure copper, this part in order to sustain this column of detectors, and also this plate is made of silicon with very pure. Okay, this is the layout, and then I discussed yesterday. Yes. What? The PMT here. What are
they reading? Which light are they reading?
they are reading the light coming from the liquid argon. So all this part is inside argon, liquid argon, and so they are sensitive to the light emitted by excimer produced from the when the release of energy you are put inside the liquid argon. This there are the production of excimer. The excimer disexcitate in the same manner that JJ discussed yesterday for the xenon. They produce light, and this light is detected or by this photomultiplier or by the this wavelength shifting read out by PSI-PM. So they see a different energy deposition respect to the germanium detectors. But the combination of the liquid argon and signal seen by the germanium detector, you will see how they complement one to the other in order to decrease the level of background events. Okay, so here in this slide I have summarized the active reduction tools. So if you select the material, you reach a certain level of background index, so a certain level of rate of background events. But if you want to go beyond this level, you have to work actively in order to distinguish between events which seems to be good events, signal events, respect to the large part of background events. And here I have shown the different topology which single out the events which are signal, if you want, respect to all the other type of background events. The signal events for us are two electron pair, an electron pair coming from the double beta decay or with neutrino or without neutrino, are single site event, so a energy deposition in a single detector and in a very defined position inside this single detector. A large part of the background behaves in a different manner. For example, there are, if a photon coming from outside the detector can hit two detectors at the same very strict time window, and this is clear a background event. So playing with the detector multiplicity, you can reject part of the background. Then there are photons which maybe dies inside a single detector, but releasing more than one energy, so making more than one interaction. And then there are events which release energy only on the surface of the detector. There are, for example, alpha, which can't penetrate inside the N plus part of a detector, which is a large part of the surface of these detectors, because this N plus is very thick, is of the order of 1 millimeter of dead material, and the alpha particle can't enter because they interact very strongly with the material. So they can only penetrate only from the P plus contact, because all the P plus contact are very thin, of the order of 100, 200 nanometers, so they are very, very, very thin. And also beta particle can penetrate on the P plus contact, or can penetrate in the N plus, through the N plus contact if they are very energetic. But as we will see, also this type of surface events can be eliminated because there are the pulse-shaped discrimination possibility that is able to distinguish also this category. So both of this multi-Compton interaction and these surface events, as we will see. And then there is another possibility. A photon can release an energy in a single, a photon can release energy in a single point of the detector and then release energy interacting with the liquid argon. If you are able to see this light, this type of events can be rejected. And this is the reason to have this liquid argon datum. And then, as I said, there are the muons, the remaining muons entering the detector can be seen also thanks to the water tank and its instrumentation. Okay, this is the last slide that I showed yesterday. So the data taking. Data taking for Gerda phase 2 started in December of 2025 and ended in middle of November 2019. These are all the various run, and this black line showed to us the increase of exposure with time. At the end, we reach an exposure above 100 kilogram per year, which was one of the goals of this experiment. So the duty cycle, so the part active of the time respect to the time is rather high, 87.7%, taking account also this part of the time in which we didn't have data taking due to the work for an upgrade of the detector, our last upgrade. But if you exclude this, you see that the duty cycle is very high, above 90%. And this is, of course, an important ingredient to have a high duty cycle because of this give directly an efficiency or inefficiency immediately. Okay, okay. Regarding the germanium detector, which type of germanium detector were used in Gerda phase 2? There was the use of 3 types of germanium detector. These are the coaxial detector, the older detector, which are the same used in Heidelberg, Moscow, are large detector of mass of the order of 2 kilogram, enriched, of course, in germanium 76. And then there are 2 types of new detector, new type, new geometry of detector, this broad energy germanium detector and this inverted coaxial detector. These 2 types of detector are of a new concept because of the new concept relies on the fact that they have a P plus contact very small. You can judge the smallness of this P plus contact. For example, these are the P plus contact, all the rest is the N plus contact. These BG are a small mass detector of the order of 500 grams, are small detector respect to the BG detector. This inverted coaxial detector instead are large mass detector. So they are in Gerda, they had a mass of order of 2 kilograms, roughly 2 kilograms, so more or less of the same mass of a coaxial detector, but they are point contact detector. So in the bottom part that you don't see of this detector, there is this small size P plus contact. So the news in Gerda phase 2 was this massive use of this P plus contact that, as we will see, this P plus contact permits to achieve to improve the energy resolution, which was already excellent with the coaxial detector, but we will see from the data that the energy resolution is improved. And then they can they are able to give to us a very simple and a very powerful pulse shape discrimination tool respect to the coaxial detector. So they have very clear advantages. So it's a step forward in this field. Regarding the number of detectors, you see that in Gerda phase 2 we had 30 enriched BJ germanium detector with this mass, 6 enriched coaxial detector, 50 kilogram, and in the last part, so after the upgrade, we had also these 5 enriched invert coaxial detector. So another improvement in these fields. Before the upgrade, we had 36 kilogram of enriched detector, and after the upgrade, 44 kilogram of enriched detector. For what concern the enrichment fraction, this detector contain 85 from 85 to 87% of germanium 76. These are the true mass containing so the mass of this detector. Only, but this if you multiply by 87%, you have the germanium 76 mass that you are using. As I have shown in the plot in the slide before, this detector are organized in strings, and here you see in 7 strings, and here you see the various detector of the various type are where in which manner they were deployed inside the liquid argon cryostat. Okay. So, words regarding the enriched germanium production. Yesterday, JJ explained the difficulties regarding the xenon procurement, and here I would like to show in which manner from natural germanium we reach a crystal. So all the stories start with natural germanium, and then producing dioxide of germanium dioxide enriched. The natural germanium is through a chemical process becomes germanium tetrafluorine or tetrachlorine, and then put in this firm, which is here is a photo from the ECP in Zelenogorsk in Russia, in Siberia. And here is a small piece of a cascade with many gas centrifuge system. And using this type of firm, you end up with this powder, which is made of enriched germanium dioxide, which is the final production of this firm. So now, due to the all the experiment using germanium dioxide use this firm in order to have this enriched germanium detector. There was essentially one provider coming from Russia. Now, after the Ukraine war, this is not more available, and now for example, Legend 1000 is working in order to have this germanium, enriched germanium from other provider. One of these is in Netherlands, so in Europe. Okay, this germanium dioxide with the germanium enriched at level of 85% or 80, so above 85%, is pure at 99.99%, so what is called 4N. This is a level of impurity very high, very high, if you want to produce germanium detector. Okay. So what you have to purify this powder. The first step is to make a chemical reduction. So instead to have germanium dioxide, you arrive to pure germanium, metallic, so-called metallic germanium. And then, of course, of this purity or impurity level. So then you have to do a purification in order, and you arrive in a first step to a 6N of pure material. And this is done with a process which is called zone refinement. So this metallic germanium is put inside a system which contains coils, which emits radio frequency wave, which melt this metallic germanium, and thanks to the drift of the various impurity, you are able to separate the impurity of uranium, thorium goes in a direction, and you remain with high purity germanium bars. And the product of this zone refinement are this bar of metallic germanium of high purity. Okay. Then this 6N is even not enough as purity. You do other zone refinement. Here are these tools of zone refinement. Here this light means that you are cooking, melting this metallic bar of germanium, and you are able to separate further the impurity. And you arrive to 11N, 12N of purity. This is the starting point to produce the germanium crystal. Germanium crystal are usual produced using this Czochralski method, in which you are a crucible, you put this germanium, you have some heater, the germanium melt, and then you, thanks to a seed, you are able to grow a crystal from this crucible. The result, the crystal is something like that, a crystal of large size and mass. Then if you study the impurity profile inside along the axis of this crystal, and if the impurity profile is satisfactory, you start to cut this crystal. And you have these different crystal slices, which are the crystal that then will be the detector. So you have this crystal slice, and then this crystal slice become germanium detector when you implement the P+ type and N+ type contact. You implant the boron in order to have the P+ contact, and you diffuse lithium in order to have the N+ contact. And this is the end of the story for the production of these germanium detectors. Of course, all the germanium detectors in the world follow the same step, except this part, of course. This part, they start with natural germanium, and they do the refinement without starting from enriched germanium detector. But all the other steps are common, are usual practice of all germanium detectors. Okay, then I said that the BG from one side and the ICP, the inverted coaxial detector, are an improvement in the germanium detector technology. And the reason is the fact that with this P plus contact detector, we have an improved, characteristic, improved performances. You can see the reason for that in this comparison. Here we have a semi-coaxial detector, so the old detector used in Heidelberg Moscow and also essentially in Gerda phase 1. This semi-coaxial detector, a section of this detector is here. The N plus contact is this one, and here the borehole is the P plus contact. There is a large P plus contact. And what happens if a photon make two interaction? So you see a photon coming from outside doing a two interaction. The holes go to P plus and the electron to N plus. And if you look to the charge signal from the P plus, this is the result. And if you do a differentiation in time of this charge signal in order to have a current signal, the result is this one from this semi-coaxial detector. What happens if instead to have a large P plus contact, you have a very small P plus contact? So you have the same interaction, a photon doing two Compton scattering, the electron goes to N plus, and the holes go to the P plus. The charge signal is this one, and the current signal is this one. So thanks to the electric field, or if you want the potential, inside the detector, if you want the energy release are stretched in time, and you can identify that here there was not only an interaction in a single place, in a single point of the location of your detector, but you have at least two interactions. So this is a clear multi-site event, so a background event. This is the principle of this work. As I said, due to the fact that the P plus contact is of a small dimension, you have a lower capacitance. Your detector has a lower capacitance respect to the P plus, a large P plus contact. This means lower noise, and you end up, from the practical point of view for us, in a better energy resolution. Okay. Which is important for the detection of neutrino stable beta decay. And then there is the other advantage due to the internal electric field. It is able to separate single-site energy deposition from multi-site energy deposition. So pulse-shape discrimination. Okay, here you see for a broad energy germanium detector and ICPC detector, a simulation, and here is shown the electric field lines. And you see that the electric field lines are converge in the P plus contact. Have this funnel effect that brings all the particles follow the same path. So the holes follow the same path, and also the electron. This is a particular characteristics of this ICPC and BG detector. The advantage to use ICPC respect to BG detector is the fact that thanks to the different geometry, you are able to build detector with higher mass with this different geometry respect to this geometry. And higher mass means that you have a lower number of detector. Lower number of detector means lower number of cables, lower number of electronics, all sources of background, as you can see, because we are not able to build cables and electronics with zero radioactive budget, of course. Okay. Regarding the exposure, how it was divided between the different germanium topology types. Here you see the PBG, the coaxial, the inverted coaxial detector. Before the upgrade, this was the amount of exposure. After the upgrade, in which this inverted coaxial was for the first time introduced, this is what we collected, and so at the end, we collect slightly more than 100 kilograms per year, summing up pre-upgrade exposure and post-upgrade exposure. And with the phase one, we end up with 127 kilograms per year. Okay. As explained yesterday by Valerio, one important point in all the experiment, and of course the germanium detector, the germanium experiment doesn't make a difference. An important point is to know the energy calibration and the stability of this detector. And in which manner we do the energy calibration of the germanium detectors. The germanium detector are calibrated inserting inside the liquid argon near the detectors thorium sources, thorium-228 thorium calibration sources with a periodicity of 1 time per week. So in a normal calibration, if nothing of strange happen, after 7 days of good data collection, you stop your data acquisition, you insert your calibration sources, you take data, calibration data for some hours. After that, you restart the normal data taking, and so. This is how all this experiment works. Then the difference depends on the type of detectors that you have. But for germanium detector, this was the choice. And so you calibrate comparing, so measuring this line coming from this thorium source. Then also you during your data taking, unfortunately, but that is the life, there are background sources which produce a gamma line, and so you are able to investigate the energy resolution that you have obtained using calibration sources with the gamma peak obtained during the data taking, because maybe one could be some misalignment between calibration and data taking. There are also another possibility. I once studies if there are shift in the energy scale between different calibration, because maybe the calibration is correct, but there are some shift during the time between calibration. Of course, this you monitor comparing the result of 2 consecutive calibration runs, and here you see the shift between two calibration, couple of calibration runs as a function of a date, using the thallium line at 2.6. This is for the coaxial detector, the BJ detector, and the ICPC. And you see that the energy shift is well inside 1 keV, well inside 1 keV, the width of the distribution. But you can also check the calibration, not only in the spanner, but the stability of the calibration, injecting pulsar signal in the front-end electronic and see if there are some instability during the time between two consecutive calibration. Or the filter, in order to have the best energy resolution, is this zero cusp filter that usually one, in order to improve the energy calibration, implement energy estimator or energy filter in order to reduce as possible the noise. Okay. And here you see instead the stability of the full width alpha maximum of the various type of detector as a function of the time. The first part before this empty is the phase 2 before the upgrade, and then the situation after the upgrade when this new detector were inserted. And you see that sometimes the upgrade is not completely positive. Maybe instead to do an upgrade, you do a downgrade. For example, here you see that for the coaxial, while for BJ, and of course for the IC, the upgrade was an advantage. Here you see that the spread is minor for the BJ, so you improve the performances. But for some, at least for one of these coaxial detectors, you see that the energy resolution was spoiled because it arrived to 10 keV. So the reason is not well understood, but the change produced some that this detector was damaged in the sense that collect more noise than necessary. But that is the life sometimes, and you have to survive with this situation. Okay. And also here you see that not all the IC detector behaves in the different manner. So the life is hard. Okay, anyway, at the end of the story, this is the big summary of the energy calibration. So here you sum up all the energy calibration that you have done in all the history of Gerda, phase 2. The energy resolution, the point are the peak detected during the calibration, the energy resolution of the peak detected in the energy calibration. The blue point and the blue line are for the PG, the red are for the coaxial, and in green for the ICP detector. First of all, you see that the improved performances, energy performances of the point contact detector respect to the coaxial detector. Coaxial detector, the energy resolution to Q beta beta is of order of 3.6 keV, and after the upgrade, the situation is not improved, is worse, 4.9, but dominated by one of these detectors. And here you see the improvement for the BJ from 2.9 keV to 2.6 keV. And this is the result for the inverted coaxial detector. So that is the situation at the Q beta beta. Okay. So now, this is the energy resolution, which is an important ingredient. And then, as I explained, the cosmic muon are rejected thanks to the muon data. Muon data, this is a photo of inside the water tank. Here you distinguish the cryostat. All the side of this water tank and also the cryostat are lined with reflective foil in order to improve the light, the possibility for the photomultiplier to see light. And then there are 66 photomultipliers. Here you see, as a function of the time, the live time of this muon veto system, and here the live day. So this detector works since 2010. Only 7 photomultipliers died out of 66 in 10 years of data taking. The muon identification remained very high. There was no dead time. So a detector which works very reliable and stable. Of course, the life is not so simple. Apart of the upgrading, which of course the detector, the data taking was stopped for the works, but we had an accident. Here there was a bad situation for the cryostat, and in order to be in a safety condition, in order to be safe, the automatic system empty rapidly the water tank. So we lose all the water because there was a bad situation for the cryostat, so it was detected a leak in the cryostat, and if there is a leak in the cryostat, the huge thermal capacity of the water will make the transition of the liquid argon in gas argon, and gas argon means that you have no enough oxygen in the hole, and all the person dies. So, and in order to prevent this, you have to eliminate the water in order to don't be in this bad situation. It was a fake alarm. So anyway, we lose all the water. And in order to restore all the water, you see the time necessary to fill this 600 cubic meter of pure water. Okay, but that is the situation. Okay, so now the data. This is an energy plot of what Gerda collected, Gerda phase 2 collected with an exposure of 104 kilograms per year. And this plot is the sum of the data collected by all the type of detectors, okay? And this plot is obtained after quality cuts, which means eliminating all the non-physical events, so discharges, noise events, and so on. Eliminating the muon, the signal induced by the muon, thanks to the muon veto cut, and also applying the anti-coincidence cut. These are only events in a single detector. Events in which you have at the same time 2 detectors which see a signal are not part of this plot. Another point you can see is that there is this region around the Q beta beta which doesn't have events. There is a hole here because around the Q beta beta there is this blind region of plus minus 12 keV, in order don't bias all your analysis cuts. Okay, so to prevent this. This region will be available only at the end when you are sure that all your cuts is well understood and there are no possibility of a bias. You can see also various interest aspects of this energy spectrum. This shoulder here is dominated by double beta decay with emission of 2 neutrinos. These are dominated. Then you see there are various peaks, not many, but there are. This is for the potassium 40, which is a contamination which is present in all the material. You see the thallium line at 2.6, another contamination of your material, and bismuth 214 comes from the uranium chain. And then at the highest part, you see this broad peak are due to the alpha decay of polonium-210 on the surface of the detector. And this high energy tail are alpha degraded. So the alpha interacts very strongly and their energy is degraded. Okay, so said this, if you calculate the background index in a region around the Q beta beta, of course, without this blind region, so from 1093 to 2190 keV, the background at this level is of the order of 14 10 to minus 3 counts per kilogram per year. This is what you can do using only the good, clean material. Lower than this is really difficult to reach. Okay, that is the situation at this point. So now is the time to switch on the active cuts. And the first cut, see. Sorry. Allora, potassium 42 is a very interesting contamination. So in the argon is made of essentially argon 40. But there is a small contamination of argon 42. Argon 42 is a very, very tiny contamination and comes from the fact that in the upper part of the atmosphere, you have a small component of a cosmic ray made of alpha particles, high energy alpha particles. They interact with the argon 40 contained in the atmosphere, and they produce argon 42. So when you obtain liquid argon, mainly produced using you bring the air and you obtain nitrogen, oxygen, and all. In your sample of argon, and then liquid argon, there is this small contamination. Argon 42 make a beta decay in potassium 42. The beta of this argon 42 has a Q value of 500 keV, so an essential. Unfortunately, the potassium 42 makes a beta decay with the Q value of around 3,500 keV, so above the Q beta beta of germanium 76. And a signal of the presence, the first observable of the presence of this contamination comes from this photon transition at 1.55 here, which say, well, this contamination is present. And it is if you don't do anything, it's a huge contamination. Your experiment is killed. And in fact, this is a story that I have skipped. When we started to put some detector in GERD phase 1, we realized the presence of this contamination. This contamination was impressive, even if the contamination at the starting point is very, very, very tiny. It was predicted by the knowledge of so of Monte Carlo. We know that there was, but it was is negligible. But as usual, the electromagnetism is a difficult part of physics. We have not realized that the potassium is a charged particle when coming from the argon, and so the electric field drift this argon near our detector. So even if the contamination, the starting point is low, but there is a multiplication factor which put all this argon, potassium 42 near the detector, and so you have this high contamination of photons and especially of electrons near your detector. And in fact, in order to prevent, to reduce, moderate this contamination, in phase 1, the string of a detector was covered with copper shroud or mini shroud, because in this manner you mechanically and instead here in phase 2, due to the fact that we have liquid argon, scintillation light, this mechanical barrier was made of transparent nylon of very high quality. But in order to mechanically protect the detector, otherwise you obtain instead to have 10 to minus 3, you obtain 14 counts. So it's impressive, huge.
Well, the first time I made the same question to Riccardo, and he explained that to me in the same terms, so exactly the same.
No, but,
and then he said, it's fine. You can study when you do particle physics, you can study quantum field theory, quantum mechanics as much as you want, but it's always classical mechanics plus one.
no, for me is. I believe that quantum physics is trivial, is the normal physics, which is very, very, very difficult, and we don't know at the end of the story, but because it is if you explain the stupid things, but we were not prepared. So. But anyway, the process is difficult to simulate, because the fields are electric fields we don't know is inhomogeneous. There are recombination process, the thermal convection. So if you want to treat from the first principle, it's not an easy task. And we didn't do, of course, because it's difficult. We are able only to do the simple things. Okay. Okay, as I said, we have the liquid argon. Liquid argon, the liquid argon veto looks like the one part, at least, in this manner. You have this fiber shroud. These are fiber, plastic fiber, scintillating fiber, covered with material which shift the wavelength of the photon. So the primary photon produced by the liquid argon are photon of this length, so they are in ultraviolet. And there are no photon detection device able to. So you have to shift to a longer length. And and here you see how it looks like, the principle of the liquid argon. So if you have a violet photon produced here, it can be seen by the photomultiplier. The photomultiplier have a cover, a plastic, some coverage, some layer, which make the wavelength shift from 127 nanometer to a wavelength matched to the photon cathode sensitivity. Or there is a possibility you produce a photon, violet, then hits this part, which is covered and, with material which reflects and also shift the wavelength, and then you see now is green and go to the photomultiplier, and the same is done, is made by this fiber, which are scintillating but also covered with a wavelength shifting. And at the top there are the these are here we have the photomultiplier, and this fiber are instead read out by silicon photomultiplier. But okay, this is for the liquid argon how it works. Here in this is also you can understand the light collection chain. So this is the attenuation length of this light in the liquid argon. The TPB is this shifting material which cover the fiber. They have 100% efficiency. Then there is the further shifting coming from the fibers. There is, which is 60%, 7% is the probability of trapping, and then the length, attenuation length of this fibers is 2 meters, and then there are other efficiency of the, so at the end, so you don't have a high probability, high efficiency to collect this photon, but you do what you can. Okay, so now you have this liquid argon veto, you have to check their performances day by day. In this plot, you see as a function of the day, the acceptance, or better, if you apply this liquid argon veto, what is the efficiency respect to the neutrinoless double beta decay, because this is a veto. A veto has no 100% efficiency, it has lower. This efficiency was checked using randomly trigger events, or you inject in your in the detectors in your detector the test pulse and see if you have randomly you are killing events, good events, or you randomly you trigger and you see the light collection of your liquid argon veto. Anyway, with a special trigger, you are able to test the acceptance, the efficiency, and you see that in the first phase, the acceptance was 98, and there was a slight improvement during the post-upgrade. Anyway, 98% is the efficiency of this system. You have also understand if your system remain stable, if the quality of your liquid argon is stable, because you are using the light of the liquid argon, and the quality of the argon make the difference. So if in your liquid argon there is a high percentage of water, oxygen, nitrogen, the system doesn't work. It's no more able to produce light. And one of the marker of the quality of your liquid argon system is the so-called measuring the triple lifetime. Yesterday, JJ said that the typical signal coming from the xenon is a signal in which there is a part coming from singlet, so-called singlet, with a very short time decay of the order of 10 nanoseconds. And then there is another part of your signal with a longer time scale, with for the xenon is of the order of 20 nanoseconds. Instead, for the liquid argon is of the order of microsecond. Okay, so a very good quality liquid argon means a triplet lifetime of the order 1.3 microsecond. Our liquid argon was not of superb quality, because you see that the lifetime was of around 1 microsecond, but we didn't do anything for the, we didn't do anything, any special operation in order to improve the quality of this liquid argon. So was at 1 microsecond, which is not wonderful, but is enough for VTOL system. And then during the upgrade, due to some bad operation, the quality of the liquid argon was slightly spoiled, and so at the end we worked in the last part with reduced 0.9 microsecond. This was some contaminant was introduced inside the liquid argon. Okay. Because there is less probability. So the mechanism, the essential mechanism is the produce of these molecules of argon or xenon. And these are this process to produce this is very delicate. If you have contaminants, they prevent the formation of this X-cimer. That is the reason. No, everything go down. There are no possibility to improve. Okay.
For example, you can start having exchange energy through thermal energy, vibration, emission of photons instead of photons. That kills the relative amount of light produced in the long, relaxed triplet tail with respect to the singlet. So the singlet is untouched, but instead of having a long range of light here, you are suppressing the light. You don't see it anymore. And so the average emission, let's say, goes towards the shorter.
And another manner to see the liquid argon stability is to select events in an energy region where you have argon 49 events, which is another contaminant present huge contaminant present in the argon, but at this energy, so not interesting for the neutrino-less double beta decay. You see that in pre-upgrade was stable, when after the upgrade it was stable, but with slightly better performances. Okay. Anyway, another manner to see how works the liquid argon veto is to see a region where is dominated by but double beta decay with emission of two neutrino. And in white, the white histogram is the previous energy spectrum. And in gray, instead, what happens if you apply the liquid argon cut? And you see two interesting points. This is the potassium 40, and this is potassium 42. Potassium 40 is an electron capture process. And so there are no energy release in the liquid argon. And you see that it is not suppressed, essentially. The pre-upgrade means that you are at 90% and 90%, 98%, which means this data is comparable with this. So this was done with artificial trigger events, and the same data and the same result you obtain with the physical data. Instead, the potassium 42 is a beta decay. It's part of a beta decay, so with large emission deposition of energy in the liquid argon, and as you see that the liquid argon makes a strong suppression of this second peak. And if you compare this part with the double beta decay with two neutrino from this curve represent the double beta decay with the energy spectrum of double beta decay using this half-life, which comes from measurement coming from Gerda. You see that in this region you remain with the number, so the liquid argon cut eliminate a large part of the background, and in this region you remain with pure double beta decay with two neutrino emission. There is there is no large space of other background. Of course, there is a background, but is strongly reduced. And here is our previous energy spectrum after liquid argon. So the gray means is the new histogram. Around the Q beta beta, before this was the size of the background index, and now it is this one, reduced. The liquid argon doesn't reduce the alpha contamination. You see that there are no suppression, and this is correct, because alpha are, the contamination is for alpha is on the surface of the detector, and of course there is no possibility for liquid argon to do anything, so this part is untouched, as you can see. Okay, then last cut is the use of a pulse shape discrimination. We have three types of detector. Two of the point contact configuration, BG and ICPC, and the other are the semi-coaxial. For what concerns pulse shape discrimination, the two different type of detector behaves in a different manner, and so you have to treat in a different manner. First, I discuss the pulse shape discrimination of this point contact detector. The discrimination here is very simple, very easy to do, and it is based on a single variable. It's a monoparametric variable. Of course, you can improve if you want, but it is enough this. And it is based on the measurement event by event of this ratio, the current divided by energy of event. In our jargon, in the Gerda jargon, is called A over E variable. E is the total energy, A is the peak of the currents. Why it is used this type of variable? Because if you have a single site events, so a neutrinoless double beta decay, independent of where the these events happens, you have this situation. You have in blue your charge, so proportional to the energy, and in green, in red, you have the current, and the current is obtained by the charge through differentiation. And you have this situation. So if you do the ratio of the current divided by the energy, you expect a Gaussian distribution at a variable, a point, at a central value, and the width of this Gaussian is dictated, dominated by the noise. Okay. Instead of a situation of the other possible events is different. For example, if you have a photon coming from outside doing multiple multiple interaction, you have a so-called multi-site event, the situation is this. You have the same charge, for example, charge signal, and if you differentiate, you see that the charge current is completely different because gives to us the information that there was a multiple site energy deposition. So if you do the ratio between the maximum of the current divided by the energy, you obtain an A over E below, of a value below the other. Instead, if you have a surface event, the situation is different. For example, an alpha can penetrate on the P+ contact, and what you see, you end up in this situation. The charge current, the current pulse is very fast and is of a higher value because not only in large part of these events, only the holes matters, not the electrons. Instead, here, not only the holes matters, but also the electrons. So both contributes, and so you have this higher signal. For the particle on the releasing energy only on the surface, for example, beta particles, you have this situation. And this is due to the fact that the N plus is very thick, and so the particle or dies inside the N plus and doesn't give any signal, or they drift in a region of low electric field and so diffuse and so take times. Part are so they have a difficult life to enter in the active volume, and so the situation is this one. The charge increase vary with a longer time respect to this rapid rise, and the current is this. So the A over E is below as a lower value respect to the signal site events. So this is what this A over E does. In which manner you exercise, so you decide the cuts, you decide where to cut. You use the calibration data. Calibration data, this is a spectrum of a calibration, of all calibration, okay, from thorium, no, the calibration used for the energy calibration. But you can use also to study the pulse shape. So here you see there is this peak, this one, which is called double escape peak, because a photon really make an E plus, E minus, so is a compton, E plus, E minus, produce a couple of E plus, E minus, the E plus annihilates, and the two photons escape. So at the end, what remain here are only two, an electron and positron. So exactly the signature of double beta decay. So this is used as a proxy of the signal. And then you have other peaks, for example, this single escape peak in which only one photon escape, or you have this, which is the full energy peak in which the photon dies, making many of these. So the double escape peak, this one, is used as a proxy for your single site event, and you check your rejection power using the single escape peak of full energy peak. Okay, this is the, here you see the, for example, in gray, sorry, in gray you see the double escape calibration data. This is A over E, but shifted at 0 in order to have a Gaussian at 0. And then you put a cut, a lower cut. You say, well, I put this in order to kill the multi-site events. And I put this in order to preserve 90% of my signal cut, of my signal events. Detector by detector, I choose this lower cut in order to select 90% of my good events. And here is the result, if you want. This in gray is the previous plot, and in blue, after applying this lower cut in order to reject the multi-site events. And you see that the signal site event remains, survive, because you have the side, 90%. And here you see that the peak of single site, this is a full site, a single site, and also the full site, full energy peak, sorry, are strongly suppressed. So it's an effective. And then you put also an upper cut up in order to eliminate the surface event, alpha events. Okay, if this is put at 3 sigma, is a number. So, okay, this is a choice. If you do this, this is result. So here you have the A over E variable versus the energy. In the point are the data of the BG and IC after a liquid argon cut. And in blue, what remains after applying this lower cut in order to suppress multi-site event, and the upper cut in order to eliminate surface events, alpha events. So remains only this blue one, which if you project on the energy, this is the result. You see that there are no more alpha. I don't know what is the suppression factor for the alpha, but it seems reasonable high. The acceptance after, so the efficiency of this cut is around 90%. Okay, around, slightly lower. But, and there are various manner in order to estimate. What remains is this, and you see at which level we reach. Okay, this is the story for the point contact detector. Yes.
What is the variability of the signal shape within a crystal? So the dependence on position.
No, in the there are no due to the internal, so you can see in two manners. If you, in the crystal, in this type of a crystal, of a detector, when you apply the external bias field, and you take into account also the fact that you have also contaminants inside the crystal, they create internal fields. So the sum of these two fields, or two potential, produce a situation in which you have high variation of a potential only around a small region around the P+ contact. Okay, all the rest of the detector, of the bulk of the detector, the potential is very, very low. So the history of the events which happens all around the bulk of the detector is the same. So independent, because of the very history happens near the P+. So here, near the P+, the holes sense a very high weight potential. And so only there they induce the charge. No? The charge is proportional to the multiplication of the induced charge is proportional to the total charge of your holes, multiply the variation of the potential. But they, due to this particular fields, electric field configuration or potential configuration, they realize this only when they are near the P+. So they are the same, this detector. Only that if you have a multi-site, of course, there is a different time of production of this energy deposition, and so you see you are sensitive to this different energy deposition. In other sense, if the events were only, supposing, only single site event, they are all similar, all equal. Apart the energy, of course, but no, of course. So it is a secondary process. There is this, but is a secondary process.
Yeah, because I was thinking that we cut based on the signal shape, is tuned on the double stick peak.
Yes.
And those events are most probably located close to the core.
No, of course. No. No. This is a very, very, very appropriate question. So I have done only a superficial treatment. No. Of course, no. Perfect. So in effect, this is only a proxy. The WXP is a proxy respect to the Q beta beta region for two reasons. First is that the proxy is 1.55, and instead the Q beta beta is 2.39, so higher energy. So there are effects, for example, there is an increase of the size of the cluster, but there is also the fact that high energy, you have more Bremsstrahlung, so you can have more probability to eject a photon, and so also a single site event is no more a single site event. And then there is another geometric factor that in order to have a double escape peak, these events are generated or located all around near the surface, we can say, not in the bulk, or not a large part are in the bulk. Instead, the double beta decay are all distributed in a uniform manner. And so we have to correct the efficiency for all these factors. this is done in various manner. We are not able to, because we don't have a deep simulation from first principle of these processes, but we take care, for example, of a geometric difference using the double beta decay with two neutrino emission, which are at lower energy, but in the entire detectors. And we take care of the energy dependence using dedicated data, calibration data, and some simulating, so using a sample and simulating. And we play with this. We have another possibility using cobalt 57, which produce so a calibration source which produce double escape peak near to Q beta beta. And so in this case, you have the right energy. Of course, you don't have the right topology, but one make some opportune mixture of this fact in order to correct maybe not so both the central value of the efficiency, but much more reliable the systematic uncertainty. Yeah. So all this is digested in large part of the work that for the time I don't touch. But this is a serious tricky point which consume person and time in order to arrive to some solid, quoted, because, okay, but this is a large part of the work. After you do this simple Pal-Chase simulation, then there is all this work, which is 90% of the real work. Okay. So this is the situation. Wonderful. Now, coaxial detector. Coaxial detector are much more difficult. You can't use A over E due to the fact that they are not point contact detector. If you simulate the current pulses for single site events, you end up with this messy situation of the current. So dependent on where the event, single site event is produced in the bulk, you have a different current, completely different. So you can't use an A over E. What is done is to use an artificial neural network, so a black box in which you exercise your network. And the input are the point of a rising part of your signal. You exercise, these are the input, you exercise with single site, multi-site, and then you end up with some cuts. So as usual, you train with single site, and then you have the multi-site proxy from the calibration, exactly as we did with A over E, but instead to use an A over E, you have a neural network. Okay, this is the response of this neural network for a single detector. This in red are the background events, in green the double escape, so the proxy of the signal. Of course, the answer goes from 0 to 1, and you put a cut, a lower cut, in order to select 90% of your signal. The time stability, for example, of this neural network for the various coaxial detector, you see, you put a 90%, this is stable. This is how you are able to reject various type of background. Okay, is stable, okay. And so if you apply this multi-site, thanks to this neural network for the coaxial detector, this is the result, the neural network answer versus energy. The points are events after liquid argon veto cut. You put this multi-site cut, which is more or less here. In gray are the rejected events, and in red what remains. And here is projection. You see there is a sizable reduction respect to the starting point. But you see that this neural network is not able to reject, is not trained to reject these alpha particles. You see that remains, and there is a contribution. So you have to invent a new cut in order to reject this new type of background that the neural network is not able to reject. And what was chosen is to give a look to the time profile of these events, how the leading edge rises versus time. And it was realized that events which deposit energy on the bottom of the P plus contact, so here, or here in the groove, they raises very rapidly in time. And due to the fact that the P plus is very thin, so the alpha enter there, and also here in the groove, which is very thin, if you cut this type of events, you cut a large part of alpha event, not all, but. And so we measure the rise time of this signal. Rise time, the usual definition, 10%, 90% of the rising part. And if the events which are faster than 180 to 220 nanosecond, of course depends on detector, are rejected because they are assumed to be alpha particles. Okay, so you apply this new cut for the coaxial detector. Okay, same plot, rising time versus energy. All the points are after liquid argon cut, neural network cut. You apply the new rising time cut. In gray are the events rejected. In green, what remains. The projection, you end up with this, and you see that there is a good rejection. Of course, eliminating these events, you pay, because the efficiency for combining these two cuts put an efficiency of a total acceptance of 70%. So 10% of events are lost. Okay, so this is the summary. This is the plot for all the detectors. In white, the empty histogram is before any active cut. In gray, after pulse shape discrimination. And in red, after also liquid argon veto cut, after all the cuts. You see that these two active cuts are very effective to reject the events. Of course, this part is not rejected because these are truly single site events, are double beta decay with the emission of 2 neutrinos. Okay, zooming in the region of interest in our analysis region. This is the situation. These are the events that we have found in this region from 1093 30 keV to 2190 keV. This is the blind region, and these are two regions which exclude because we know there are peaks, so we are not important. And the result after all cut is this one. These are the small number of events that remain. And the background index is 5 10 to minus 4 counts per keV per kilogram here for the full data taking. So now we are sure that we have done everything. We are sure of all our cuts, we have checked, we know everything. We can open the blinding region, but and also only at the end of this procedure where all the cuts were well understood and nothing can be changed. Whatever you see, we find inside this gray region, we have to accept. We can't change anything. And this is the result. So you have some events here, but you see there are no events, no counts. You can see this is at 2.4 sigma, this the nearest count. So this is the final spectrum that we have found after 100, more than 100 kilogram per year. So now, what are the final background index? These are the background index for the different detectors. You see that within the large uncertainty, we see the same background index. Okay, this is the situation. So now you have to extract the final information. So from the plot, you see from this plot, you see that we don't see any signal. Okay, we don't have to do many discussion. You see, you have to do you have to extract the limit. So you have to do at the best. So what we have done is to make a partition. So which means a group of data from a single detector in stable condition with stable parameters. We divide the life of a single detector in partition, so where the various parameters which define the life of a detector in a stable condition. We use a single background index because they are the same. And so we do the analysis using this partition. The partition means this, for example, for these are two so this is a detector, a BJ detector, and this is another BJ detector. This is the full alpha maximum, so the energy resolution, and this is the energy shift. You see that the energy resolution of this detector remain stable in the pre-upgrade period and then in the post-upgrade, and also the energy shift. So this is the normal situation with the two partitions, one which describe the pre-upgrade and the other the post-upgrade. Other situation can be this. For example, for this, there was this shift. So we have divided in 3 parts in order to take into account that there was this shift, energy shift. Okay, due to some hardware changes or whatever. Okay, so you do this unbinned maximum likelihood fit, assuming that the background is flat. The Monte Carlo simulation say that the background is flat around the Q beta beta. Okay. And so this is the only assumption that we do. And then that the signal is Gaussian with opportune width. We have 13 events, single background, and systematic unsteady are taken into account. Anyway, systematic uncertainty plays a minor role in this analysis, only 2%. This is a worsening of the 2% respect a poor statistical analysis. So we did a frequentist, a Bayesian, because there are religious members, of course, believers of two different religions. The frequentist is based on this two-sided test statistics based on profile likelihood. Description of the method is here. The Bayesian is described in this. Anyway, for both, no indication for a signal, of course. The upper limit is for the frequentist this one, and for the Bayesian this one. The median sensitivity, so without the presence of a signal, is coincide with the upper limit. This is only the situation, and the same also for the Bayesian. The background index from the fit is this, estimated this one. If you want, and then you can, this half-life, usually use this one, you can translate into m beta beta, which maybe is a parameter of relevance, at least in order to compare the result, the final result of the experiment is in this range. The range comes from the nuclear matrix element uncertainties. Of this, if you go to the usual Vissani plot in which you have m beta beta respect to the lightest neutrino mass, this range is outside. Gerda is not able to enter inside the inverted order hierarchy. You are above. So, but it's a very important result. Okay, so I would like to finish here with this plot, which is really the Gerda legacy. Yesterday, I think JJ stressed the fact that it is difficult to reach an experiment background free. Okay. Here is the proof that Gerda is or was the first experiment background free. Why? Because you see that the half-life increase linearly with the exposure, which is the real sign that this is an experiment background free. Here we have in green the sensitivity, which comes from Monte Carlo simulation, knowing the performances of the experiment, assuming no signal. And you see this. And the red are the result of the experiment. Of course, you see that the result fluctuates in respect to the expected for no signal, because it's a random extraction. Between many experiments, we have realized Gerda. But apart of the fluctuation around the expected signal, you see that there is an increase of the half-life with linearly with the exposure. So this is okay, the main achievement of Gerda. At this point, I want to introduce, because this is important then for the next lesson, the other important experiment that I have only cited at the very beginning yesterday, which is the Majorana demonstrator. Majorana demonstrator are the other, the brother of Gerda. We had many connections between Gerda and Majorana community in many years, developing all the detector technology. And as I said went yesterday, the philosophy of Majorana demonstrator was different, an alternative to Gerda. So to push the cleanness of the material at the highest level. And using a compact, a more traditional and compact layout. So you have these two cryostats filled with your detectors, which are in vacuum, okay? They are refrigerated thanks to this finger, okay? And then around you have a very ultra pure copper. All the structure for the in order to pile up these detectors and also the cryostat is made of ultra pure copper. And then you have an inner copper shield and lead and bricks and so on in order to protect the detector from the environmental radioactivity. A very, very important point is this ultra pure copper, which is made, is electroformed copper, made underground, so without any cosmic activation. So is a very the purest copper ever produced in the world. And here you see the various pieces. And of course, they use also the pulse-shaped discrimination. So the result, to be brief, is this one. In gray, you see the data after data cleaning, muon rejection, multiplicity cut, the usual cut. And then in gray, you see here, is after eliminating surface events, alpha events, you can say. And in red, after applying all the cuts, so at the end, the multi-site cuts remain the gray. And here you see the zoom around the Q beta beta and what remains in red. The exposure of this experiment was 71 kilogram. The background index was worse, slightly worse respect to the Gerda. The energy resolution was 2.5 keV. They used a point contact detector, only point contact detector, and they reach the best energy resolution. No signal, lower limit 8.3, 10 to 25 years, median sensitivity, and the upper limit is slightly worse respect to that. And the data were completed in 2021. So that is the end of my story for today.